Hello, everyone. Thank you all for being here. I'm Jasmin, and I'm coming from the Laboratory for Carbon Nanostructures. And today we're going to talk about the Raman spectroscopy. So the key in understanding the Raman spectroscopy is in its name, because since it is a spectroscopic technique, it means that we are going to be analyzing or we are going to be using the light-matter interaction. So thanks to the light, we're going to be analyzing the material itself. So how do we do that exactly? So we take a sample of interest and we shine it with a laser, and then some of this light from the laser is going to be scattered, right? And what are we looking for is the difference in the energies of the scattered light and the incident light. So that means that we are not interested in elastic scattering, and that's the majority of our signal, and that's something that we want to remove. So we are not interested in that. But the inelastic scattering is something that we are interested in, and we want to see by how much the energy has been gained or the energy has been lost. And this goes through a series of components inside the equipment, such as diffraction grating, CCD camera, amplifier, and it comes to your screen as a series of peaks. So on the y-axis, you have the intensity of these peaks, while on the x-axis, you have the wave number. Now, to understand the origin of these peaks and to appreciate the Raman spectroscopy, we have to go into the physics, into how these peaks come about. So the Raman spectroscopy is based on the molecular vibrations. So which means that if you excite a molecule with a laser, and for example, it goes to a higher virtual energy state and then goes down to the same state from where it started from, that means that you're having that elastic scattering that we mentioned that you're not interested in, and here it's called Rayleigh scattering in the picture. But occasionally what happens is that as you shine the laser on the sample, the bonding electrons get displaced, and you create a momentary polarization of the molecule. So it's a very short time, it gets polarized and then returns to its original or to a slightly different state. Specifically, if you find a molecule that is on the ground state, you excite it to a higher virtual energy state, and then it goes back not to the original state, but to a slightly higher vibrational energy state, then that means that you're having energy loss, and that's what we call Stokes-Raman scattering. In the opposite scenario, if you have a molecule that you find it's already at an excited vibrational state, and you excite it to a virtual energy state, and then it goes back to a lower vibrational energy state, you have a net gain in energy. And that's something that we call anti-Stokes-Raman scattering. So based on the amount of energy that has been lost or gained, you obtain these peaks here that are in the Raman spectrum, there. And knowing the intensity of this peak, then you know that that in your sample you're having a certain amount, a certain types of vibrations, and you know how much of that is there, and that tells you a lot about your material itself. For example, the common example or application of Raman spectroscopy are the nanocarbons. We're talking about graphenes, about the nanotubes, nanofibers, graphite, and whatnot. And in general, in case of carbons, we are looking for so-called D band, G band, 2D band, maybe RBM bands. So these are all bands of certain vibrations. For example, the D band arises when you have a breaking of the symmetry in your perfectly crystalline structure of graphite. So these atoms that are at the edge of this structure are going to vibrate different and have a different vibrational energy than the atoms that are in the middle of this perfectly crystalline structure. And the vibration mode, or the vibration type, we can call it, of these atoms that are in the middle, we call it a G band, and it's here. And instead, the D band is at the edge, and it's here. So we can see that we're having the two different bands that are being presented because of different vibrations. And then you can do a lot of other things. So if you analyze these peaks and if you check their intensity, their width, and the ratios and the shifts and whatnot, You can get information on the concentration, you can get information on the stress of the material, if there is doping, crystallinity, and so on. And you can use it for many different materials, such as solids, liquids, and gases. Now, regarding the technical picture, there are many manufacturers. The famous ones are Thermo Fisher, Bruker, Vitek. The picture here shows the Vitek Raman spectroscopy that we have in our own lab. The price is usually around tens of thousands of USD and has a resolution of 1 micron in X, Y, and Z directions. But this can be pushed a bit better depending on the purpose and by using some specialized Raman spectroscopy techniques such as resonance Raman spectroscopy, micro Raman spectroscopy, surface enhanced, and so on and so on. So here you have some links for further reading, and if you have any questions, I'll be happy to answer them either now or later through email. Thank you very much.